My name is Clinton Davisson. After working under professors such as Robert A. Millikan, Owen W. Richardson, and J.J. Thompson, I was always fascinated with the idea of quantum mechanics and their projects with quantum mechanics, inspired also by Louis de Broglie's hypothesis that the nature of matter is wave-like. My colleague Lester Germer and I set out to test this hypothesis at Bell Labs in 1927. What we did was we designed and built a vacuum apparatus for the purpose of measuring the energies of electrons scattered from a metal surface. Electrons from a heated filament were accelerated by a voltage and allowed to strike a nickel surface. The electron beam was directed at the nickel target, which could be rotated to observe angular dependence of the scattered electrons, and our electron detector was also mounted on an arc so that it could be rotated to observe electrons at different angles. It was a great surprise actually to find that at certain angles there was a peak in intensity of the scattered electron beam, and this peak was what indicated wave behavior for the electrons. In our experiment, Germer and I assembled an apparatus similar to what might be used to look at the interference pattern from X-rays scattering from a crystal surface. The basic idea is that the planar nature of crystal structure provides scattering surfaces at regular intervals. Thus, waves that scatter from one surface can constructively or destructively interfere from waves that scatter from the next crystal plane deeper into the crystal. So when X-rays are scattered from a crystal lattice, peaks of scattered intensity are observed. If the crystal structure is known and the diffraction angle is known, then a wavelength can be determined. Our experiment was designed to send an electron beam with an adjustable energy to a crystal surface, nickel, and then measure the current of electrons detected at a particular scattering angle. If this was to show a characteristic shape indicative of an interference pattern and consistent with the planar separation in the crystal, then we would have dramatic proof of the wave nature of matter. In an attempt to test de Broglie's hypothesis, we ended up proving the wave nature of the electron. The Bragg law for diffraction had been applied to X-ray diffraction, but this was the first application to particle waves. Yes, the experiment actually occurred in Bell Labs, room 7B, located in the West Village of Manhattan in New York City. In 1927, the year that I conducted the experiment with my partner Lester Germer, the first transatlantic telephone call was made from New York City to London. Lindbergh made the first solo, non-stop transatlantic flight. The first live demonstration of television occurred at the Bell Telephone Building, and the last Model T Ford was produced. Also involved with the project was Lester Germer, my partner at Bell Labs. However, the British physicist George P. Thomson also discovered the same phenomenon, that electrons can be described as waves, and as a result, we shared the Nobel Prize in Physics in 1937. I led the project assisted by Lester Germer. This experiment represented a major step forward for quantum mechanics at the time by proving that electrons behave like waves. After this experiment, I continued my research and soon contributed directly to the development of the electron microscope. In addition, as a result of the project, the APS Davisson-Germer Prize in Atomic or Surface Physics is awarded in alternate years in the areas of condensed matter physics and atomic, molecular, and optical physics. Yes, in 1928, I was awarded the Comstock Prize by the National Academy of Sciences. In 1931, the Elliott-Cresson Medal by the Franklin Institute. In 1935, the Hughes Medal by the Royal Society in London. And in 1941, the Alumni Medal by the University of Chicago. In addition, I also hold honorary doctorates from Purdue University, Princeton University, and the University of Lyon and Colby College.